In this video, we will use Excel to calculate various measures of variability, including range, variance, and standard deviation for a set of scores. In the two videos that follow this one, we'll talk about calculating measures of variability and frequency distributions and grouped frequency distributions. But for now, we're working with a straight set of scores, or observations as they're sometimes called. As with previous videos, I've uploaded a practice Excel sheet that goes along with this video. Feel free to follow along with your Excel sheet to help you to work out these calculations. Okay, so to calculate measures of variability, we're going to start with a set of scores right here. And here are 11 scores or observations. And the first measure of variability we're going to discuss is the range. And the formula for range can be seen right here. Range equals the highest score minus the lowest score in a distribution. And so I'm going to calculate that for this distribution. And as you can see, we've already arranged the scores from highest to lowest. So I know which is the high score and which is the low score. So I'm going to say equals the high score minus the lowest score. And that gives us a range of 8. And so a range is just a real quick and easy way of getting a sense of what the spread of the scores might be. I know that there are 11 scores and the range is 8, so that gives me some indication of how they might be spread out. But if I had, instead of an 8, an 80 for the top score, it would dramatically change both my range and my mean. And so with the addition of just one outlier score, the range becomes something else altogether. And so the range, as you can see, is very sensitive to outliers and therefore isn't a very precise measure of variability. And so I'm going to return us back to where we were with our range of 8. And the next measure of variability that we're going to talk about is the mean deviation. Here's the formula for mean deviation. I see that sigma letter right there, the Greek letter sigma, which tells me I'm going to sum up whatever comes afterwards. And it looks like I'm going to be summing up scores minus the mean. So let's see what that looks like over the total number of scores. Okay, so what I have to find out first is this score minus the mean for the denominator, or numerator, excuse me. So I'm going to go over here to my scores, and I'm going to take the first score, and I'm going to subtract the mean that I've actually already calculated using Excel's average function. And this tells me that the score of 8 deviates by 3.73 units from the mean. So the score of 8 is 3.73 units away from the mean. I want to go ahead and fill in the deviations for the rest of the scores, but I need to tell Excel to keep the mean part of the equation constant. So I'm going to put a $sign before the B and a $sign before the 15. And now I'm going to drag down and we will have all of the deviation scores. So a score of 5 is 0.73 units away from the mean. A score of 3 is 1.27 units below the mean because we have a negative number here. So we have some negative numbers and some positive numbers. Now if I sum these deviations, let's see what happens. And I came up with 0. You might have been able to guess that actually. The 0 doesn't tell us very much. It's 0 because of what the mean is. The mean is the point in the distribution of scores that lies in the center. So all of the scores that are larger are offset by all of the scores that are smaller. Essentially, the problem is that half of the scores are negative and the other half of the scores are positive. So we have to somehow get rid of the negative signs, and there are a couple of ways to do this. The first way is to find something called absolute values. Absolute value is another way of saying eliminate the negative sign. And there's actually an Excel function for absolute value. And so I want to find absolute values for these numbers. I'm going to put an equal sign. I'm going to insert a function. I'm going to type in absolute. And nothing came up, but I'm going to go ahead and click down to all categories. Sometimes that happens. And I see ABS, and ABS returns the absolute value of a number without its sign. So that's definitely what I want. And the absolute value I want is of 3.73, and hit return. And we have the same number, 3.73, because The positive number will look the same as the absolute value. There's no sign associated with it. But let's see what happens when we drag this down to the other numbers. Okay, so through the magic of Excel, all those numbers that were negative now no longer have a negative sign. And so these are absolute values that we're looking at. We're going to sum up these absolute values. And now we'd have a non-zero value of 24.73. And this number now represents the numerator in the mean deviation formula. This is the top part right there. The denominator is going to be the number of responses, which I know is to be 11. So if I'm looking for the mean deviation, I'm going to do an equal sign. I'm going to press on this for the numerator and select 11 for the denominator. And we end up with a score of 2.25 for the mean deviation score. This tells us that each score is an average of 2.25 units away from the mean. But there's another way that we can get rid of negative signs that's actually much more common in statistics. That is, we can square the numbers and find something called the variance. And I have the formula for variance right here. If you will recall from earlier math learning, a negative times a negative gives us a positive, just as a positive times a positive gives us a positive. So regardless of whether our number is positive or negative, when we square that number or multiply that number by itself, the result is positive, and that will help us to get rid of the negative numbers. I've created a column here for squared deviations. We're going to take the deviation scores and square them, just like we're asked to in the formula. So I have equals the first deviation score. I'm going to insert what's called a caret by hitting Shift and the number 6, and then I'm going to put the number 2. A caret and 2 mean to raise that number to the second power or to square it. So when I put a caret and 2 next to 3.73, I'm squaring 3.73. And it gave us a lot of pounds, so I'm going to make sure I have this with 2 decimals. Number 2 decimals. Okay, all right. When you end up with a lot of pounds, it might mean that your decimals are going on for days. And so 3.73 squared gives us 13.89. So I'm going to drag down to find the squares for the rest of the deviation scores, and then I'm going to add them up at the bottom. Okay, so now we have the numerator for our formula for variance here. We have the sum of the squared deviations right here at 76.18. And in looking at the formula, what we're going to do then is divide by the number of responses, 11. So for the variance, I'm going to put an equal sign. I'm going to click on the sum of squared deviations. I'm going to put that over 11, and we come up with what's called a variance of 6.93. This number tells us that, on average, each score varies from the mean by 6.93 squared units. You'll recall that we squared the deviations, so this could be confusing when it comes to interpretation. For example, let's say the unit we're looking at is years. What is 6.93 squared years? If the unit we're using is a pound, as in a pound of weight, what is 6.93 squared pounds? Because of this problem with interpretation, we often take an additional step to take the square root of the variance, which turns our units back into their original form. And this is referred to as standard deviation. The standard deviation is the most common measure of variability presented in most academic papers. Below is the formula for standard deviation, and you can see that it's represented with the letter S. And this is why variance is represented by S squared, because the standard deviation is the square root of the variance. So once we've calculated variance, calculating standard deviation is pretty easy. We simply take the variance and find the square root. And to find the square root in Excel, we can use the Excel function for square root, so we will do that. Equal, insert a function. I'm going to type in the word square root, and I end up with SQRT, which does return the square root of a number. That's exactly what I'd like. and I want to find the square root of my variance for this, and I end up with a standard deviation of 2.63. This means on average a score in this set of data deviates from the mean by 2.63 units. If we're using year for the unit, for example, we would say the average score deviates from the mean by 2.63 years. The mean deviation and the standard deviation, as you can see, have similar interpretations, but have slightly different values due to the slightly different ways that we calculated them. I'm going to share with you one more way to find variance and standard deviation that might be simpler to calculate. Your textbook refers to this as the raw score formula, and this can be a bit simpler in that it requires fewer columns for calculations. So we're going to look at the raw score formula for variance, and as you can see, the numerator in this case is simply the sum of each score squared. So I can create a x squared column, and I can square the scores themselves by putting an equal. The score, if you will recall, we'll put a caret and the number 2, and we have 64. And I noticed that I know that 8 times 8 is 64, so I've done that correctly. And I'm going to go ahead and pull that all the way down. So these are the squares of all the scores. And as we look at the formula, there's the sigma, which indicates that we're going to sum all of those squared scores. So I can do that as well. And I end up with 277 for the sum of the scores squared. So we have the numerator, 277, we have the n, that's going to be 11, but what we don't have is the last part of the formula, which is the mean squared. So let's do that very quickly. We know the mean was 4.27, so the squared mean is going to equal 4.27 raised to the second power. Oh my goodness, and I ended up again with a lot of those. So let me quickly format the cell. Don't want 13 decimal places, for goodness sakes. And we end up with a squared mean of 18.26. Now I'm going to insert a new row so we can compare if our variances are the same with the two different formulas. All right, so we have all the numbers we need now for the raw score formula for variance. We have the sum of squared scores. So I'm going to first put an equal sign and put the numerator over the denominator, which is the number. And then I'm going to minus the squared mean. So we have all three parts, three numbers needed, and we wind up with exactly the same variance using the raw score formula as we did with the previous formula. Variance is the same. And if we were to square this, we would end up with the same standard deviation as well. I want to point something out. You'll notice that I didn't need to put parentheses around the division term, and that is because division in this case would be done first before subtraction, and that's exactly how we wanted it to happen. And so in this case, I didn't need to use parentheses to separate out any of the terms. So now you have two different ways of finding the variance and the standard deviation. One was sort of the, I won't call it the normal way, but it's the standard way, and then there's also the raw score formula for finding variance and standard deviation. And it's just going to depend on your own preference. The advantage to using the first set of equations is when we make our final calculation, we just simply need to divide by one number by another. But we have two columns, and that can be problematic. The raw score formula only requires one column, but the final calculation is just a little bit more convoluted. So be sure to try both formulas to see which one you're most comfortable with. And you might want to try practicing with the practice assignment problems 1 and 2 right now while this information is fresh in your mind. And then tune into the second video where I will discuss calculating measures of variability in a simple frequency distribution.